Greetings and welcome back. Today we'll be looking at a video about identifying isomers. That is to say, how is the relationship expressed between any two molecules. So for this we have really 5 options, and we'll be looking at those 5 options one at a time. Alright, the first option is when they have no relationship whatsoever. And what we do for this, or kind of the easiest way to define this, is that it is not the same molecular formula. So the same molecular formula indicates that it has the same amount of each thing in there, so the same amount of carbons, the same amount of hydrogens, the same amount of oxygens. So in order to check this, what I would do is just kind of basically count up what's in that molecule. So if you see something like this, right, so this guy has an OH right there on a wedge, and something like this right here. The simplest way to do this is just to start with the rare things. They both have 1 oxygen, so that's correct. But the guy on the right specifically has, let's see, 1, 2, 3, 4, 5 carbons. This one has 6 carbons. So before you go any further, you just know that they have no relationship whatsoever. We would say that these are both alcohols, but they have no relationship, they don't have the same molecular formula, and then you're done. You don't need to worry about looking at R or S or name or anything like that. If they don't have the same number of carbons and hydrogens and oxygens, then you're good. A quick way to count for the same number of hydrogens is if they do have the same number of carbons and they do have the same number of oxygens, so let's say that this guy does have a 6th carbon, you can go through and count up all the carbons if you want to, all the hydrogens if you want to, but an easier way is just to check the elements of unsaturation. If they don't have the same number of elements of unsaturation, they will not have the same molecular formula. Alright, that's it for no relationship. Structural or constitutional isomers is something we've talked about in pretty decent depth, so I won't spend a lot of time on these. These guys would have the same number of elements of unsaturation. They would have the same number of, nitrogens, carbons, oxygens, all of that good jazz. So if we went through and added up the amount of stuff in there, we would find that they have the same amount. So this would be C6, N, and the H's would be, oh, how quickly can I do the math? 6.5 times 2 plus 2 would be 15. I think that would work out. Oh wait, there's 1 element of unsaturation. So there should be 13 in there. Alright, let's check that and count that out really quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, that's great. This guy would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So both of these guys would be C6, NH13. Or C6H13N is also probably the better way of writing this. But these guys would therefore be structural or constitutional isomers because they do have the same molecular formula, but the molecules are not joined on the same place. Same molecular formula. All right, but the same stuff is not attached in the same place. And I think it's fairly obvious for these examples. But to give you something a little bit closer, if we had something like this with an OH here compared to something like this with an OH down there, the way that we would number these two compounds is that the one on the left would be a hexanol with the alcohol at number 2. The one on the right would be an alcohol which would be a 3-hexanol. So those would be different molecules. We haven't gotten to the point of worrying about the wedges or the dashes or the R's or the S's or anything like that, but they have the same molecular formula. It's just that things are attached in different places. All right, the third variety of this would be enantiomers. And as you know from the last few weeks in class, the simplest way to look for these is enantiomers are compounds where one is R and one is S. So these are specifically a version of stereoisomers, which means to say that they do have the same molecular formula, of course. They have the same stuff attached in the same places. So you would have an alcohol at the same spot. So let's say 1, 2, 3, 4, 5, 6, and I've got an alcohol right here. And this guy would be 1, 2, 3, 4, 5, 6, and it's got an alcohol down there. So these guys are enantiomers. They would have the exact same name because the bonds are in the same place. So this would be 2-hexanol. And this would also be 2-hexanol. But we could go through and do the R's and the S's really quick. This guy would be 1, 2, 3, and therefore go clockwise, and we would say that this guy would be R2-hexanol, and then this one must be S2-hexanol. So enantiomers have the same molecular formula. They've got the same number of atoms. They're in the exact same places. They're bonded the same. The only difference is a wedge versus a dash. Or in the case of a Fisher projection, it could be that one is on one side and one is on the other. So for instance, we could have a Fisher projection that looks like this, with CHO on top, CH3 at the bottom, Cl on the right, and an H on the left, as opposed to something that has a CHO on the top, CH3 at the bottom, an H on the right, a Cl on the left. And we could go through and do the R's and the S's on that, but these guys have bonds in different places, so therefore their relationship to each other is that these guys are enantiomers of each other. All right, the last real relationship is diastereomers. So diastereomers is another version of stereoisomers where they differ only in R and S. Differ with R and S, but it's only possible with more than two, or equal or more than two chiral carbons. All right, so what that means is that we know if we have exactly one chiral carbon, then something is either going to be R or S, and therefore it can only have an enantiomer, which is the other version. So if it's R, your enantiomer would be S. But what if you have something that is, let's say, 2R, 3R? Then the enantiomer of that, I'll just write enantiomer, I'll stop there, would be something that is 2S, 3S. A diastereomer would be something that is, for instance, 2R, 3S. So they are still related, but they don't have the same, they're not exactly opposite. So another version of a diastereomer would be, it could be 2S, 3R. In all of these cases, you have one compound. Its enantiomer would be exactly the mirror image, where all of the chiral carbons are flipped. A diastereomer is if you compare this guy, one or more of the carbons are flipped, but not all of them. This is the kind of thing that we most often see in terms of Fisher projections with multiple chiral carbons, which we've looked at before, and that might have one thing switched but not another. So let's say, for instance, I've got an OH here, H there, OH here, H there. I'll make this guy an aldehyde at the top, so CHO, and I'll put a CH3 at the bottom. So the mirror image of this, or the enantiomer, would have everything switched. So both of your chiral carbons would be moved around. And so we would say that these guys are related as enantiomers. All right, but the other possibility would be to have some of them switched, but not all of them. So if I'm comparing that one at the top, a diastereomer of that might have still the CHO at the top, still a CH3 at the bottom, but I would have an OH on the right at the bottom, and H on the left at the bottom, and maybe I've got both of my OHs on the same side. So these guys would be related as being diastereomers, because if we look at the beginning one, I've got OH top left and OH bottom right. If I exactly flip that, it would be bottom left and top right. Those guys would be related as enantiomers. For it to be the same molecule, I need to have the OH top left and the OH bottom right. But if I've got both OHs on the right, it's neither an enantiomer nor the same thing, But it is a stereoisomer because it still has the same number of atoms. They're still joined the exact same way. They only differ in terms of wedges and dashes, or from right side to left side. All right, so that's how we define diastereomers. Again, diastereomers can only exist if you have 2 or more chiral carbons. The last option would just be simply the same molecule. Hopefully that one's fairly obvious. There are multiple ways to draw the exact same molecule. So if I had this guy right here, and you saw that there was this molecule right here, you were asked to figure out the relationship of these things. You could take your time and rotate it around in your head. You could rotate it around on an axis. Or, to me, an easy thing is to just figure out the R and the S. So this one would be 1, 2, 3, which is R. This would be R2-butanol. And the one on the right, this O is number 1, this is number 2, and that's number 3. But you may recall that if H is in the front, we draw our arrow from 3 to 2 to 1. And so this is also R, so this is also R2-butanol. So of course there is the possibility that 2 molecules might be exactly the same thing, and usually on a piece of paper you wouldn't see them being drawn in exactly the same way. So you might have to do a little bit of rotation. But the last relationship is that they could of course be the exact same molecule. So the way that I gave these to you is probably what I would suggest you do, is to go through the options of looking for, first off, do they have the same number of atoms? If so, keep going, but if not, you know that they have no relationship whatsoever. The second thing would be to look for, are bonds attached in the same places? And if they're not, but they do have the same amount of stuff, that is to say the same number of carbons, the same number of elements of unsaturation, then they're going to be constitutional or structural isomers. Everything after that is stereoisomers, where the only thing that differs is a wedge versus a dash. If everything is switched, they're enantiomers. If some stuff is switched but not everything is switched, they're diastereomers. And if nothing whatsoever is switched, they're just exactly the same molecule. All right, so those are the possible relationships between molecules. And thank you very much. I will see you in class.